Hey everyone, Miss Folk here, and we are on our last section for chapter 13. So you are on 13.6, and this is all about mutually exclusive events, okay? So for our first definition here, I already wrote it out. Our mutually exclusive events can't happen at the same time. So what I mean by that, like an example would be picking an ace or a king. You can only pick an ace or you could only pick a king. They can't occur at the same time, okay? So your formula for mutually exclusive, remember before with independent and dependent, we had probability of event A and B. This is going to be A or B, okay? And so to draw that, that's using a U. Basically means the union of A and B. And that's equal to the probability of A plus the probability of B. So we've already kind of done that. Most of your basic probability are mutually exclusive events, okay? So nothing too new here apart from the actual name itself. So for not mutually exclusive events, an example of this could be, let's say, adopting a cat and a mammal. Or a mammal, I'm sorry. Or is with your mutually exclusive. So, or a mammal. Clearly, a cat is a mammal, so this can happen at the exact same time, okay? So your formula for this is going to be your probability of A or B, or again, A union B, and that's going to equal to the probability of A plus the probability of B minus the probability of A and B, okay? And our last definition here is the complement, which we've talked about before. I've mentioned that in a couple of your other notes, but all that really means is the word not. So here I have not A, as if A was an event. Okay, so an example of that, if A was roll a 2, you're not A. The only thing that might be different, I don't think I said it, if you put this line over A, that means it's the complement. So if you ever see that, that just means not A. And again, we would just write roll not A2, okay? Or not roll a 2, I guess would be better English, but that's okay. So for a couple of examples here, I want us to decide if they are mutually exclusive or not and why. So we have drawing a card that is an ace or a 4. This can't happen at the same time, so this is going to be mutually exclusive. And again, our reasoning can't happen at same time. An ace can't be a 4, and a 4 can't be an ace. All right, for drawing a card and getting a jack or a diamond, this can happen at the same time, so it's going to be not mutually exclusive, okay? And again, we could say our reasoning would be jack can be a diamond. In fact, there's one jack of diamonds in a deck if you want to be really specific. All right, we got rolling a pair of die and getting a sum of either 6 or 10. That can't happen at the same time. There's no way to roll two numbers and get two different sums. There's only one sum. So you could write there's only one sum, or you could just write, oops, can't be 6 and 10. And I should say at the same time. And our last one here, we have raising your hand and walking in a circle. Don't know why you'd want to do that, but could you at the same time? Absolutely, if you really wanted to. So that's going to be not mutually exclusive, and our reasoning again can happen at the same time. All right, so hopefully that's making a little bit more sense. So not mutually exclusive, it can happen. Mutually exclusive, it cannot. All right, so moving on to your next page here, we have to determine if the events are mutually exclusive or not, and then find the actual probability. So for our first one here, we have drawing an ace or a heart from a deck of cards. So whenever you're dealing with these kinds of questions, it's really good to automatically write whether it's mutually exclusive or not. So can we have an ace and a heart at the same time? Yes, we can. So this means that it's going to be not mutually exclusive. So remember, going back up to your formulas here, you're not mutually exclusive. We need 3 separate things, okay? So I'm going to go ahead and define my event A as being an ace I'll say B is my heart. And then our probability of our event A, getting an ace. Remember, I did say you need to know your deck of cards. How many aces are there? There's 4 of each kind of card. And remember, there's 52 cards in that deck. So our probability of A is going to be 4 out of 52. Our probability of B is going to be 13 out of 52. Remember, you have 13 of each kind of card, so 13 hearts, 13 hearts, diamonds, clubs, and spades. And then our last thing we need for not mutually exclusive is our probability of A and B. So how many cards are an ace and a heart in a deck? There is only one ace of hearts, so it's going to be 1 out of 52, okay? And for our final step here, our probability of A or B, and you do have to make sure you're actually labeling all of these, okay? So our probability of A or B, we're going to add our A probability and our B probability. So 4 out of 52 plus 13 out of 52. And then we're going to subtract our and, so our 1 out of 52. And if we do that, we get 16 out of 52, which simplifies down to 4/13. Okay? And that is one thing I was noticing on some of your guys' work. Make sure you're always simplifying to that, or to the smallest terms, okay, if you're leaving it in a fraction form. All right, now number 2, we have rolling a die and getting a 6 or 2. So again, can we get a 6 and a 2 at the same exact time? No, we can't. So for this one, this is going to be mutually exclusive, okay? So we need just our A and just our B probabilities. So I'm going to say A is getting my 6, B is getting my 2. On a regular dice, my probability of getting a 6 is just 1/6. Same exact thing with my probability of getting a 2, that's also 1/6. So my final answer, my probability of A or B, is going to be 1/6 plus 1/6, which is 2/6 or 1/3. Okay. All right, I am going to let you guys do this next one on your own. And again, the key will be posted, so make sure you see the key for this one, okay? But moving down here to number 4, here's a lot of your problems for mutually exclusive and not mutually exclusive are going to be using these frequency tables, okay? So here we said, it says to fill out we already filled out the table. I pretended we did already, okay? So we want to find the probability that a person eats breakfast or wears contacts. So again, can those two events happen at the same time? We'll say eating breakfast is event A and wearing contacts is event B. Do they ever intersect? Let's check. Here's my eating breakfast. Here's my wearing contacts. Yes, they both touch in this bar. So since they can occur at the same time, obviously that is going to be not mutually exclusive, okay? So we're going to have to define what our event A is, define what our event B is, and find our probabilities. So I already said A was eating breakfast, B was wearing contacts, so I'm going to go ahead and jump right to the probabilities actually. So our probability of A, of eating breakfast, we have to do a couple of things first. We have to see how many people eat breakfast altogether, and then the total number of people in this survey. So I'm going to go ahead and total up all of my tally marks here. Here we go. So for eating breakfast, if I were to add all of those up, my total for breakfast is 13. My total for not eating breakfast is 11. And my absolute total would be 24, okay? Now, technically, I could add up my totals on the right side here. So wearing glasses, I have a total of 4. Here I have for contacts 11, and no glasses or contacts, I have 9, okay? And again, if you want to double check, add everything up, make sure you get that 24. So for our probability of event A, so eating breakfast, by itself, there were 13 people eating breakfast, and again, we found that there were 24 people altogether. And then for event B, wearing contacts, if we look over here, I had 11. So 11 out of our 24 wear contacts. Now remember, for not mutually exclusive, we also need to find the probability of A and B. So that's where they both occur. So again, if it's easy for you to visualize, that's fine. Or I like to always highlight where do they intersect. Clearly it's right here. So we can see that our probability of A and B occurring, so eating breakfast and wearing contacts, is 4 out of 24. So our final answer, remember we want to find the probability of wearing contacts or eating breakfast. We're going to add 13 24ths, our probability of A, plus 11 24ths, our probability of B, and then we're going to subtract our probability of A and B, so that 4 24ths. And when we do... Okay, sorry about that. I realized I had a mistake on my key. But as I was saying, we should have 13 24ths plus 11 24ths minus 4 24ths. And if we do that, we get 20 24ths, which simplifies down to 5 6. Okay, so moving down here to number 5, the rest of this page actually is not really going to be focused strongly in your book, okay, but I did want you to see these kinds of problems. So we have consider a deck of cards. What is the probability of picking a king or a heart? Use a Venn diagram. So I know you don't actually need the Venn diagram to do this kind of problem, but it's good to know how to use Venn diagrams because sometimes you'll just be given a Venn diagram and have to do the problem that way, okay? So the reason I'm starting off here with a box, you always want to make sure you're doing that with probability, especially with mutually exclusive events, because here I'm going to label one of my circles king, one of them hearts, obviously. And then down here in the lower right-hand corner, you're going to put the amount of cards that don't qualify as a king or a heart, okay? So first things first, we know that we have 4 kings in a deck of cards, okay? For hearts, we know that we have 13. Now, since we have a king or a heart, can those occur at the same time? Yes. So how many hearts or kings of hearts are there? So I'll say that, kings of hearts. How many are there? There's exactly 1. So I'm going to go ahead and put that 1 in the middle of my Venn diagram right here. Okay, it's always good to start with the very middle of your Venn diagram. So since we know that we have 4 kings, okay, I see that I have that 1 right here in the middle, so that means that I'm going to put my other 3 in this remaining king part of the Venn diagram. Same idea with my hearts. I see that I had 13. I already have 1 accounted for, so the other ones I'm missing are 12. Okay. Now if we add those together, so 3 plus 1 plus 12, we get, what is that, 16. So we know that 16 cards are kings or hearts. So that means down here in the lower right-hand corner, that leaves 36 cards remain out of our deck, okay? So now we have a Venn diagram that's representing our entire deck of cards, and specifically the kings and the hearts. So now that we have that, we're going to go ahead and find the actual probability, okay? So again, our events are getting a king or a heart. So a probability of getting a king, we know there's 4 of them, so that's going to be 4 out of 52. Our probability of getting a heart is 13 out of 52. And then again, using that Venn diagram, I'm just going to say A and B here. Using that Venn diagram, or we knew the deck of cards anyways, we see that there's exactly 1 that occurs in both of those. So our final answer, our probability of A or B, so I guess I should have said this is my A, this is my B. Our final answer is going to be 4 out of 52 plus 13 out of 52 minus that 1 out of 52. And if you do all that correctly, we should get 16 over 52, which again simplifies down to 4/13. Okay? Now, like I said, we clearly did not need the Venn diagram for this problem, but sometimes you'll be given that Venn diagram and have to work backwards. So that's why I wanted us to practice writing one at least. Now for number 6 here, we're also going to see problems where we use a tree diagram to find probabilities. So looking here, we want to find the probability of a Twix given that a female picked it, okay? So remember, this line right here, that just means given, okay? So what is the probability of us picking a female who has picked a Twix, basically? Well, let's look. Females, we see that there's 511 females. So how many out of those females picked a Twix? Given that we have a female, how many picked Twix? We can see that 100 picked our Twix. So our probability is going to be 100 out of 511, since we're dealing with just given that it's a female, okay? And for our next one here, our probability of picking a Reese's given that a male has chosen Reese's as their favorite, we'll say. So let's look at I'll do in red here. Male, we have 470. How many preferred Reese's? We can see that that's 190 out of 470. And this one we can simplify down if we divide by 10, 19 over 47, okay? So that's just how you read those kinds of problems as well. And one of your Edulastic problems looks just like this, okay? And finally, our last question here. So it says, not use a survey, use this survey. So this survey was conducted between girls and boys on choosing between the colors red and yellow. The results are posted below. So again, remember this 20 down here in the bottom right, that's saying that 20 people weren't female and didn't pick the color red. So that means basically 20 males picked yellow, okay? So our probability of selecting a red given that they are female. Let's take a look here. Clearly we can see for females altogether, we have 21 and 13. So I'm going to add that up. Females, we have 21 plus 13, which is 34 total females. Okay, so you have to make sure you're adding both the numbers that are just in that female part and the shared ones. Okay, so we have 34 females, and we want to see how many picked red. So clearly, right here, this 13 is in that shared red circle. Okay, so we can see that 13 out of our 34 females picked red. So our probability of getting a red, given that they're female, is 13 out of 34. And then for the probability of just having a red selected, all we have to do here is see how many people chose red. So I'll do a different color. Let's look. Here we had 16 people that weren't female chose red, and we had 13 females choose red. So altogether, we had 16 plus 13 choose red, which is 29. And now here's where we have to be careful. We know 29 people chose red, but we need to make sure we find that total number. So our actual total number now is we just have to add up every single number here. So 16 plus 13 plus 21 plus, you can't forget this 20 down here. That's all the people that took the survey, okay? So if we go ahead and add all of those up, we should get 70. So our final probability is going to be 29 out of 70 people selected red, okay? So hopefully that makes a little bit more sense. You do have, I think, maybe one or two questions like these ones on this back page on your Edulastic assignment, but please let me know if you have any questions at all.